Okay, now we'll have a very quick discussion about rectifiers with filter. Okay, with filter circuit. See, why we are using rectifier? Basically, we are using rectifier so that we can convert AC quantities, AC. Suppose the voltage is AC. After rectifier, our aim is that we should get DC. And what is the ideal waveform shape of a DC? See, this is the ideal DC waveform. Ideal DC waveform. Okay, so this is this kind of waveform we desire to get out of a rectifier. Fine, but see, with if we consider the half wave rectifier, if the input is sinusoidal half wave rectifier, and what kind of output we get, means output voltage how will we get? We'll get like this, right? So if you compare this with the ideal case, we can see it is not the same. It is still DC. It is still DC, but it is not, no way it matches the ideal DC waveform. Okay, so, what we can do so that it may not be exactly ideal waveform, but little bit it will be close to DC waveform, ideal DC waveform, but better than what we are getting the output of this half wave rectifier. Okay, okay, so for that, to smoothen out this pulsating DC, we can use filter at the output of the rectifier. Fine. So one of the simplest filter is a capacitor filter. Okay, simply we'll connect a capacitor across the load. Fine. So I'm not drawing the half wave rectifier circuit here. So suppose this is the input and suppose this is the output. So output we are connecting this R load. Okay, okay, how this half wave rectifier basically looks like? Here diode will be connected. Okay, so this whole thing I'm showing it as a showing it's inside this box half wave rectifier. Okay, at the output terminals what we can do is that we can connect a capacitor. Okay, and this capacitor will act as a filter. Capacitor filter. So after connecting the capacitor, what it will do is that will somehow somewhat smoothen out this DC waveform. So this yellow line is the output of half wave rectifier with capacitor filter. Okay, so this will be the waveform. So you can see that after the capacitor filter, it is little bit better. It's little bit close to the ideal waveform. Not obviously it's not close, but better than before. Okay. So similarly, if you consider a full wave rectifier, similarly you can connect this kind of capacitor. Suppose full wave rectifier. What is the output of the full wave rectifier looks like? Looks like this. Okay. So now suppose inside this box the full wave rectifier circuit is there. This is the input side. So here also we can connect the capacitor. So after connecting the capacitor, we will see that get waveform like this. Okay, much better than before. Okay, this is the full wave rectifier with capacitor. Fine. Now suppose if you could design a capacitor very efficiently, you have tuned the value of the capacitor very much, and maybe extra components also you connected with the capacitor. So maybe a inductor you connected. So basically this filter, various types of filter configurations are there. So suppose we have designed a filter circuit very well. Okay, suppose we have suppose this is a full wave rectifier. So suppose here in parallel you connected a circuit. I don't know what kind of circuit looks like. A combination of capacitor, maybe inductor, maybe some other kind of active devices. I don't know now. At this point I don't know. I'm simply writing this filter. Okay. A very highly efficient filter. Okay. So before the output looks like this. So if you can somehow manage to build some such kind of filter, you may get output like this. Okay, full wave rectifier plus very efficient filter, right? This is the ideal filter. Okay, so we'll see that you will get the output very close to the ideal DC, the best case scenario. Okay, so if you can manage to build such kind of filter circuit, so then if you calculate the ripple factor, you will see that the ripple factor is 0 because there is no ripples. What would be the conversion efficiency? Conversion efficiency will also be into 0. Okay, because for a ideal DC, the average value, RMS value, both are equal, and if both are equal, the conversion efficiency and the ripple factor will be both at its highest value. Sorry, not the highest value, means the efficiency will be the highest value at 100%, and the ripple factor will be at the lowest value, that is 0, means no ripples. Fine.